Greetings. In the previous video, we managed to cover the mass conservation and first law of thermodynamics for the heat exchanger problem at hand. Now we shall move to the second law of thermodynamics. Well, our next step is to write down the second law of thermodynamics for our three control volumes. Let's have a look at the equation. This is the equation for the second law of thermodynamics, and as we know, the left-hand side is 0 since the problem is steady and nothing changes with time. There are inlet and exit paths which bring with them inlet and exit entropies. There are heat transfer in two cases and there's no heat transfer in another case. We have to decide on the boundary temperature, which we shall discuss it shortly. And there is a stat-gen, which of course we have heat transfer. We have a stat-gen, but we have to discuss what this stat-gen means and where does it apply, how does it act. So what I would do is to just simplify this equation and try to understand its different terms for our problem at hand. Now, the second law, now we want to write the second law. The second law for the water side, which is this one, for the water flow, is 0 equals m dot water times Si minus Se, inlet and exit entropy, plus Q dot water divided by boundary temperature, which is not the same because the inlet temperature and exit temperatures are different. So we have to make an assumption for this boundary temperature plus S dot Gen. Now, for oil flow, for the oil side, we would have a very similar equation, and that is 0 equals m dot oil times Si minus Se plus Q dot oil divided by Tb, which is different from this one since the temperatures are different for oil plus S dot Gen on the oil side. And finally, for the heat exchanger, we have 0 equals m dot water, times Si minus Se, which is the change of entropy in this stream. This is for the water side, plus m dot oil times Si is not a dot, it is Si minus Se, and that is for the oil side, plus S dot Gen, and there is no heat transfer for the heat exchanger to the surrounding. Heat exchanger has no heat transfer to the surrounding, so Q dot over Tp would be 0. Now, let's see what terms these equations have and how we could calculate them. A very important point is how could we calculate Si minus Se. And the equation we have for calculating entropy, this is a single equation, this is the second Gibbs equation, and it is TdS equals dH minus vdP. This is the second Gibbs equation, which is very key because this equation just relates entropy to other properties, and that is key for us. The problem is constant pressure for both water side and oil side, so this term vanishes, and therefore ds would equal dH divided by the boundary temperature, the temperature of the boundary that happens. Or at this time, before we integrate it, we have to write it T, and then we could write it then as TB once we have integrated. ds would be, or delta S would be SI minus SE. These are capital letters which indicate the extensive property S, and that equals HI minus HE divided by the temperature. What is HI minus HE? You see, this is Q dot. We have written an equation for this one, and we have come to an equation for this one. Therefore, what we can conclude from this is that S dot gen should be 0 for the streams themselves. Okay, for the streams themselves, S dot gen should be 0. It doesn't mean that S dot gen is 0 between the streams, but we have assumed no reason, no irreversibilities inside this stream. All the irreversibilities are between these two streams where the heat transfer occurs. As for this stream, it is just the flow that moves in and then moves out. Whatever entropy change that happens in this stream is because heat is taken out from it. This is the entropy transferred by heat transfer, and not the entropy generated due to irreversibilities. So the do here is that we calculate this value. We calculate this value. Calculating it is very simple. Vs would equals Cp times dt over T, and integrating it, Si minus Se equals Cp ln Ti over Te, and for the water side, m dot water times Si minus Se equals 9100 divided by 3600 times 4.18 times ln 533.15, which is the value 260 degrees C added with 273.15 just to make it kelvins, divided by 423.15. And the outcome for this would be 2.4416 kilowatts per Kelvin. This value is this term. In fact, now we have calculated this term to be 2.4416. 2.4416. This is the value we have calculated for this term on the water side, and we know that this equals this term with, and this term cancels out inside the water. So the water loses entropy, but due to heat transfer. Now, as for the oil side, as for the oil flow, m dot O times Si minus Se equals 27,300 divided by 3600 times 3.55 times ln 303.15 and divided by 346.35. And the outcome would be minus 3.5865 kilowatts per Kelvin. What is that? This value is here. We have calculated this value, and this is minus 3.5865 here. So we have terms of this, we have calculated terms of this equation, and we know Q, and now we could put more discussion in it. You have also calculated the terms in this equation. This term is also, this one is 2.4416, and this term is minus 3.5865. We have all these values, and let's see what they give us. Well, the first and very straightforward answer that we could get from these equations is from this one, because we have all terms here, and we could just calculate S dot gen. Here, S dot gen would equal 1.145 kilowatts per Kelvin, which is the entropy generated in this heat exchanger, in the total heat exchanger. This in fact includes the entropy generated due to this heat transfer between two different temperatures. So this is the overall heat entropy generation of this heat exchanger. Once we have cancelled out these two terms, as I mentioned, now we can have a sort of not average, but equivalent temperature. So equivalent temperatures. What we are now calculating is equivalent boundary temperatures. Equivalent boundary temperatures. This is what we are now calculating. And as for the water side, TB for water would be just calculated from this equation. This value is 1162. This is 0. So we could calculate TB to be 476.04 Kelvin. This is the equivalent temperature. You see, when you want to calculate a boundary temperature for such problems, what we do, we take the inlet and the exit and divide them by 2. We add inlet and exit temperatures and divide it by 2 and say this is an average boundary temperature. But we could also calculate an equivalent boundary temperature. We know that average is not accurate. It's fairly good, but it's not accurate. If I calculate the average temperature, TB average TB for water would be just add the two values, 260 degrees and 150 degrees, divided them by 2, and that would be 478.15 kelvins. This is the average between inlet and exit temperatures. That is 260 plus 150 and divided by 2, which makes it 205 degrees C, or it makes it 478.15 kelvins. You see, these two values are very close together. Very good approximation here. Also, we could calculate an equivalent boundary temperature, TB for oil, and that would be from this equation, just put 1162 here and calculate TB, and TB for oil as equivalent would be 324 324.1 kelvins, 324.1 kelvins, and if you just average the inlet and exit temperatures, TB average, the average temperature would be 324.7 Kelvin. So they are fairly similar, fairly close values as they are. You see, alternatively, if you wish to just not put S such as 0 and calculate it, you had to assume a value like this one for TB, and you would gain a very small value for S dot gen, which would be ignorable generally. But this is the better approach to calculating the average temperatures for from this equation and this equation for water side and oil side. Now, there are another 2 points to cover. Well, there are 2 further points that we may discuss for this problem. First is that if I assume a system here with this blue boundary where there is no mass transfer through it, no mass enters or leaves, and it just accepts heat from the water side and delivers it to the oil side, then that system should contain all the irreversibility of this heat exchanger. So if we write the second law for this system, you see, the second law for this system, would be 0 equals Q dot water divided by TB water. This is that equivalent temperature that we once discussed, plus Q dot oil divided by TB oil, and plus S dot gen, which is the generated entropy for this heat transfer between two boundaries of different equivalent temperatures. And so we know all the values for this equation, and 0 would be 1162.3, and this is positive because although water is losing heat, but this system is gaining heat through in the water side. So this should be positive, divided by 476, 476.04, which is its equivalent temperature, plus now on the oil side, this new system is losing heat, so it is minus 1162.3 divided by its equivalent temperature, which is 324.1, and plus S dot gen. The value we would calculate for S dot gen from these two equations is the same as before, and S dot gen would be 1.145 kilowatts per Kelvin. And this is the same study from a different point of view. And the final point that we need to discuss is that these are two temperature sides to the heat exchanger. We assume the parallel flow, so both um, uh, sides would enter, move parallel, and exit. Uh, I mentioned that there could be a counterflow heat exchanger, but let's see how that would look like. Now, parallel flow heat exchanger, they won't be just assumed. If you just assume that this is x, which is the length of the heat exchanger, and this is T, which is the temperature, then here is the inlet. Assume that this is the inlet, and this is the exit. Then as for the water side, this would be 260 degrees C, which is here, and this is, say, 150 degrees C, and the water side moves like this. This is on the water side. On the oil side, it enters at 30 degrees C and leaves at 73.2 degrees C, and therefore the oil side would look like this. There's a sharp temperature gradient between the two sides to start with, but both end fairly close together. This is a parallel flow heat exchanger. This is called a parallel flow heat exchanger. Now, if we had arranged a counterflow heat exchanger, it means that oil had entered from this side and had gone counterflow to the water and had exits from this side. Then the diagram would look like this. This is temperature, and this is the length. This is inlet, and this is exit. Water would be the same. Say it is 260 degrees C, and this is 150 degrees C, which is this one. 150 degrees C, let it be here. And now, as for oil, it would be 30 degrees C here, and 73, 73.2 degrees C on the other side. So it would look like this one. Water flow would be in this direction, and oil flow would be in the other direction. So there would be an equal temperature difference throughout the um, throughout the heat exchanger. In this case, there should be some temperature difference at the two exits because um, there should be some heat transfer, still some heat transfer at every point. In this case, even the exit temperature for oil could be higher than the inlet temperature for water, and this should cause no problem since the um, since the uh, still at its exit there is still a temperature gradient where there could be heat transfer. Okay, I hope you learned from this solution, and thanks very much for watching, and cheers.